Hello, everybody. My name is Shishi, and I also go by the name Ethan. And today I'm presenting my paper on the title of Clinically Relevant Predictive Modeling for Personalized ACL Reconstruction Classification. And before I get started, I wanted to talk a little bit about the motivation behind this research. So ACL injury is a pretty common problem, and it becomes a very severe problem actually in the United States. Every year, more than 250,000 surgery was performed annually in the United States for ACL injury. And the biggest issue is during the ACL reconstruction, actually the rehabilitation, when they enter rehabilitation program, the assessment for return to sport is primarily rely on the subjective clinical test. And this kind of assessment lacks the precision to track individualized recovery progress or offer clinically explainable insights to tell are they actually ready to go back to sports or not. So some of the related work, like traditional return to sports decision, you can see they often relies on cognitive load tasks and movement quality tasks or motor performance tests. And these kind of subjective clinical tests it lacks the precision and standards to tell whether the patient is actually ready to go back to sports. And another method is researchers used IMU-based method to extract features and use those extracted features to train machine learning models to predict ACL reconstruction outcomes to tell if they are actually ready to go back to sport. But one of the issues is that the machine learning were treated as a black box, so it eliminates the interpretability to explain it in a clinical relevance way for clinicians to make an informed decision. So our approach, first of all, we included two sets of ACL reconstruction outcomes. One is left injury versus right injury, and one is injured group versus healthy group. And we placed 5 IMU sensors on the participants. You can see on the wrists, on the ankles, and on the sacrum. And we have the participants walking and jogging on the treadmill for the 2 activities. And we extracted the data based on 10-second timing window. And our first hypothesis is that if we used phase slope index-based features, which basically represents the causal relationship between different dimensions of the IMU sensors, the assumption is that if we use phase slope-based features, the machine learning performance in terms of predicting ACL reconstruction outcomes would be improved significantly. And second is we believe the hypothesis is that we believe important sensor pair patterns is different between walking and jogging phase. And third is we not only just want the model performance, we also wanted to interpret the model confidence on each data points and correlate that with the patient specific characteristic for interpretation. So the first result we have is after we extracted the PSI features, we performed a frequency filtering method based on 8 Hz and 16 Hz and 32 Hz to see which filter applies the best. And we performed the classification on left versus right injury and also healthy versus injured group on the 5 different models, include SVM, naive Bayes, random forest, KNN, and neural networks. And we see that when we use the 16 Hz frequency filter with the KNN model performs the best across all cases. And we don't want just only the performance, we want the interpretation. So the first thing we did is from the trained KNN, we performed the permutation importance analysis based on sensor pairs. You can see each of the block is 1 pair of sensor. And we see during the walking phase for left versus right, you can see more than one sensor pair exhibit as important pairs. But for jogging, there's only one, which means that walking shows a broader variability and makes it difficult to predict, and hence jogging is a much better task suited for ACL reconstruction prediction task. And same thing was observed in the healthy versus injured group. And another thing we did is from the dimension reduction perspective, you can see from the left-hand two figures, one is the top one was the walking phase, and the bottom one is the jogging phase. And it's colored based on either this person is left injured or right injured. And one interesting observation is that jogging shows a better class separation compared to the walking phase. And another observation is that you can see from the right-hand side figure, which is colored by the model confidence. And we see that low model confidence data points tend to cluster in the center of the plot. So the same observation was found in the healthy versus injured group. So we wanted to see why this is happening. How is this observation linked to the patient, right? So we took a look into the patient characteristic, specifically looking into the month of recovery. And this is the pairwise relationship between the coherence of each patient during the walking phase and the jogging phase to the month of recovery. And we see that, you can see from the very right of this figure, when the month of recovery is longer, the coherence tend to get better. This is actually makes sense because high month of recovery tend to lead to you are walking and jogging in a more like a normal person, which makes the model difficult to predict if you are left injured or right injured, right? But this way we can present it in a more visualized and quantifiable way for the clinicians to see if this person is actually recovered or not. And also, we looked into just the month of recovery itself and categorized them based on the model confidence. And you can see the orange box plot is the model with higher confidence, and the with a lower confidence. And you see that when month of recovery is higher, the model confidence tends to get lower. So the conclusion of this research is that, first of all, PSI-based features would help significantly on the ACL reconstruction classification task. And second of all is the jogging task provided a more discriminative gait patterns than the walking phase. And third is the month of recovery is significantly linked to the gait pattern for ACL patients, and it's also directly linked to the rehabilitation progress. Yeah, thank you.
Thank you, Yusen, for sharing this inspiring work. And now, everyone, please join me in welcoming our next presenter, Philip, from Stanford, and who will be sharing his work on the dynamic for computing on LLM. Let's give applause to him.
Should I just use my computer on? Because they're totally empty. Oh, let me quickly grab my Mac. Sorry.
I guess so. Yeah, he's gonna use his laptop.
Let's do it like that. Yeah.
Would you have configured his laptop? Did you test your laptop?
No, because I wanted to present it like that. But Perfect. Test. Perfect. So sorry for the quick interruption. Yeah, hi, I'm Phil, and I'll present my paper about dynamic LLM execution in fog environments. So once again, an AI paper. Of course, the clicker doesn't work right now. So introduction, as we've heard a couple of times today already, the amount of data created through wearable devices, digital health apps, EHR systems, grows exponentially in the last couple of years. And these kinds of data points can be used to enhance care delivery, patient engagement, and clinical outcomes. And that has been proven tons of times and makes sense, right? Yet, the efficient representation and utilization of these data points remains challenging because these data formats are very heterogeneous, they're very unstructured sometimes, making it difficult to have actionable insights derived from them. So enter AI, large language models. These models are very good in bridging the gap between complex raw data and meaningful, human understandable, human readable, actionable insights. Meaning, it has been proven that LLMs can answer questions, summarize, interpret structured or unstructured text data very, very well. And that serves as a great tool for health use cases. However, deploying these kinds of centralized AI systems, LLM systems, in practice remains challenging in the health field. Because first of all, trust, transparency, privacy, right? Because you're kind of sending health data, very sensitive health data, to some black box system in the cloud. Regulatory compliance comes with that, and of course, high cost. If you scale such a system to millions of users, you will run into quite limiting cost factors. And that has been shown a couple of times already. So we need a paradigm shift. What can we do? We shift the LLM execution from these kinds of centralized cloud environments closer towards the user in a dynamic fog computing fashion. What does it mean? Let me illustrate. So in a very usual sense, we have a large amount of end customer devices like a phone or a Mac that communicate with cloud-based language models. Best example, OpenAI. However, as we've seen, you run into trust, privacy, cost issues, especially in the health domain. So what can we do? We can shift the execution totally towards the edge device, towards the local end device of the user, meaning an iPhone, a watch, a Mac. Obvious problem with that is limited computing power and the not being able to use larger models for these kinds of inference environments. So is there anything between these two layers? And here is where fog computing and the fog computing paradigm comes into play. Fog computing refers to an architectural paradigm that positions so-called fog nodes closer to the user with quite respectable computing power. Meaning, in our case, in the health use case, we could deploy such fog nodes in a clinic or in a hospital. That allows users to utilize these network local resources for their inference tasks in the medical space. And if we draw a triangle around these kinds of layers now, you see from a cardinality perspective, you have a couple of very powerful centralized AI services, and you shift that kind of focus closer towards the edge of the entire network, which represents the user devices. And with these kinds of layers, these kinds of three layers, with that architecture, you can now use and cleverly combine these layers to perform your respective tasks. So the quick formal definition of fog computing, it's an extension of edge computing, which I think most of the CS guys here know, and strategically positions substantial computing resources closer to the data sources through these intermediary fog nodes, as I've mentioned. We have the three layers, the edge layer, the fog layer, and the cloud layer. Edge layer is a customer device that generates and utilizes data. The fog layer is positioned strategically between the cloud and the edge, and they host substantial computing resources. And the cloud layer, a centralized unit of substantial computing power. However, as we've mentioned, problems regarding privacy, trust, and cost. So if we now want to use such an architecture in a use case, in an application, in a medical application, you run into the problem of complexity, right? Maintaining such a system, communicating with that holding state, that's all very hard to implement. meaning we want a very unified LLM agnostic interface that transparently is able to allocate inference tasks across all of these 3 layers based on the complexity of the task, meaning the size of the model that is required, and the data sensitivity. Meaning if you have a very data sensitive task, you can perform that locally. If it's not that sensitive, you can do that in a fog or in the cloud. And the key goal here is to being able to cleverly combine these types of different layers and utilize their strengths and compensate their weaknesses. So we instantiate this entire approach in SPASI LLM. SPASI LLM is part of the stands for SPASI Digital Health Swift-based ecosystem, meaning we support the entire Apple stack from a Mac to a watch to an iPhone. It's fully open sourced, MIT licensed. You can find that here on GitHub. I'll get to a QR code in a second. And the approach that I described before is totally implemented here in that framework and ready to use. In general, the SPASI ecosystem contains tons of modules like onboarding, account management, Bluetooth medical devices connection, and of course LLM execution, as I mentioned. And these layers that we've talked through before, these fog layers, are now represented in code in these types of targets. Meaning we first of all have the cloud target that integrates with the most common cloud providers of LLM services. First and foremost, OpenAI, but also Anthropic and other services. We have very nice convenience components for tool calling, function calling, DSL, domain-specific language, and so on. For the fog layer, we have the benefit is a kind of trade-off between the privacy of data and trust with the ability of the model. We decentralize or we position these decentralized fog nodes within a local network, for example, a clinic, and then use them to perform our inference tasks. And lastly, the local model, or the local layer, is, as mentioned, directly executed on edge devices. We have here kind of the gold standard of trust and privacy, financial soundness, because we can reuse existing distributed infrastructure. However, the downside, obviously, very limited computing power. So, as mentioned before, the unified, transparent LLM agnostic interface is what really stands out here in this framework. We can totally transparently talk to all of these different layers without the user having to worry about the technical implementations. I'll keep the technical details very short here in this presentation, just one quick walkthrough regarding the dynamic dispatch of a fog node or of a task to a fog node. We have 2 main components here, which is the client, which is, for example, an iPhone, and then the server component, which is reflected like as the fog layer on the fog node. And if a inference task comes in, we, on the client, discover the respective service via MDNS in the local network. We then connect to it via TLS, via a custom CA. We authorize that request if the client is actually able and authenticated to do that operation on that fog node, and then we stream back the model response via the OLAMA framework. And the key part here is that we're able to totally mirror any kind of API that uses the OpenAI API, which is like the de facto standard for these things. Now, to the results, we've now used SPASI LLM in over 10 1 minute, right, to go, perfect. In over 10 applications. In the paper we mentioned 6, but since the submission we expanded a bit. I want to quickly highlight Health GPT and LLM on Fire. Health GPT enables you to chat with your local Apple Health resources in your iPhone with a local model, with an OpenAI model. And second, LLM on Fire on the very right, which enables you to chat with your Fire EHR resources, again, via different layers of models. And of course, a quick performance characteristic is that sure, these centralized models are faster, they have better benchmarks on specific medical tasks, but the fog node and the local layer are good in their own sense. That means if you use them carefully and for respective tasks, you can definitely do that and perform actual things. The interesting thing is like the inverse relation between context size and inference speed, especially on the limited availability of main memory on the local layer. The interesting thing here also for local devices is if The model architecture is optimized for a specific chip on an iPhone. The model parameter size is actually not the key limiting factor. It's the actual architecture. The Spatial LLM framework serves as the foundation for various other papers and research that we did. It enables it. This is kind of the underlying foundation. And yeah, here are some resources, and thank you for your attention.
Thank you, Philip, for envisioning and implementing this new paradigm. Thank you. Our next speaker, Yang Wang from Georgia Tech, will be talking about a very novel work on user nicotine intake estimation. Let's give applause to Yang.
Hello, everyone. I am Yang, and I go by Diana. I'm currently a PhD student at Georgia Tech, and today I'm presenting you Puffum, an e-cigarette sleeve for estimating user nicotine intake. So vaping is a growing public health concern. There are more than 83 million electronic nicotine delivery systems, or also called ENDS users worldwide. And those often have a lot of risks, including harmful chemicals, nicotine addiction, and developmental concerns. And not only they would affect users, but also their bystanders. So this underscores the pressing need to monitor and understand ENDS consumption patterns for the development of effective strategies to support vaping and smoking cessation efforts. And there are some challenges currently with it. There's a lack of robust tools to measure vaping events. A lot of people currently use self-report. However, self-report can be very inaccurate because of memory inaccuracies or delayed reporting. And other tools include wearable sensors like a smartwatch. However, they would often misinterpret everyday actions, for example, eating, which has the same gesture as smoking. And among those tools, they also have limited utility. For example, they may not be versatile to work with multiple devices or offer other clinical utility like nicotine estimation. Therefore, we propose our system, Puffum. It has several key contributions. It is a modular and highly adaptable system compatible with various ENDS devices. It offers a novel approach for estimating nicotine intake using magnetometer. And we also did a pilot study demonstrating the potential of detecting vaping behaviors and show support for smoking cessation interventions. So how would our system work? This is the working principle. As the user inhales, the pressure changes, and then the heating circuit would send current to the wire, and the increased airflow would lower the temperature, and the current increases to reach the target temperature. And this cycle will repeat as the user continues to inhale. And the changing current generates electromagnetic field because of physics principles, and our magnetometer can sense that EMF, and then the wire heats up and the liquid vaporizes, and that's the complete cycle of one puff event. So to enable that mechanism, we designed a PCB board that included those key sensors. We have a touch sensor, an IMU sensor, and a magnetometer sensor. The magnetometer sensor is placed on the back for proximity to the device. And how it works is we design an enclosure, and it's wrapped around a copper tape, and that copper tape is connected to a wire and connected to a touch sensor. And when the user touches the device, the touch sensor would confirm device interaction, and then the magnetometer sensor would detect the fluctuations in the ENDS electromagnetic field. So when the user is vaping and Puffum is activated, it will start to send data over Bluetooth Low Energy. Therefore, we designed a complementary mobile app to collect that data in real time. And we also collect a bunch of other mobile sensor data, for example, location, timestamp, activity status, screen on, off. And by having the system being able to collect data in real time, that also enable us to do other kind of data collection. For example, whenever a puff event is detected, we can also do an ecological momentary assessment to collect the real-time stress and craving levels. So to evaluate our system, we did comprehensive lab testings. Firstly, we did puff detection. We use a phantom lung to emulate human inhalation and exhalation behavior to do more reliable testing. And we recorded 5 consecutive puffs and recorded magnetometer signals. So we analyze the signals within the puff frequency range and apply a baseline threshold. And the peaks here illustrated as the red dots are the detected puffs. And we can also calculate the area under the curve of the magnetometer sensor data that is shaded in yellow here, which would enable us for further analysis. So when we were doing the puff detection, we were wondering, can we use that magnetometer area under the curve to classify the puff intensity or the volume of air being inhaled when users are vaping? So we place an air pressure sensor inside the phantom lung and simultaneously record the air pressure changes and the magnetometer data when when the phantom lung is vaping. And we assess the correlation between the air pressure changes and the magnetometer readings during puffs. And we can see there's a strong correlation with R squared equal to 0.99 between the inhaled air volume, that's the area under the curve of the pressure readings, and the magnetometer area under the curve. Similarly, previous research also estimated nicotine consumption by measuring the weight before and after vaping. And they did this because the liquid containing nicotine that was being vaporized is directly correlated with the weight. Therefore, in our study, we did a similar approach and measured the weight change before and after 5 puffs and repeated that for 5 times and see a correlation between that with our magnetometer area in the curve. And again, we observe a strong correlation with R squared equal to 0.96 between the magnetometer data and the vaporized liquid weight. So all of that testing was done on a popular ENDS device called Joule to demonstrate if our device can work with different kinds of electronic cigarettes. We also tested on other popular brands called Vapresso and Caliburn. And this is a signal-to-noise heat map. And the darker the area is, the higher the signal-to-noise ratio is. So the grids illustrate the different places we place the magnetometer on the device. So we can see that we're able to get high signal-to-noise ratio at different locations across multiple devices. So in addition to that, we also wanted to enable our system to support longitudinal studies. So we did an energy consumption test. An e-cigarette user vapes approximately 365 puffs a day on average. Therefore, we calculated how much our device can last with a coin cell battery for average users vaping 200 puffs, 300 puffs, and 400 puffs a day. And we can see that with just the magnetometer data, our device can last over 2 weeks. And with both the IMU and magnetometer sensors, our device can still last over a week. So in addition to the lab testing, we also did a small scale in the wild pilot study. We did that with 2 participants recruited from the university, 1 male and 1 female. And we asked them to use our device in their daily lives for 5 days. By applying the similar signal filtering techniques we did on tests, we were able to extract 753 puffs across 41 sessions. That's 5.79 hours in total of data. And our system also allows us to look at more granular vaping behaviors. For example, we can calculate the intersession intervals, which was shown to be correlated with craving levels in previous research, and also the interpuff interval that was shown to correlate with other mental health behaviors. For example, people with schizophrenia has shown to have a shorter interpuff interval and higher nicotine intake. So our system can allow future research to leverage it and do a more granular analysis of people with different mental disorders and analyze their smoking behaviors. So in our user test, we also asked them to finish a system usability scale and a user burden scale after using our device. So for the system usability scale, a score of 68 is the typical benchmark, and both of our users indicates above average perceived usability. And for the user burden scale, the top 15% has a score of A, and the next top 30% will have a score of B, and both of our users also indicate our system has low user burn. So here are some directions for future research. In our user study, user has reported that there is no visible feedback when data is being recorded. So future research could try to improve on the privacy features. And we also included an IMU sensor on the board, but we haven't used it. Future research could leverage it to detect fidgeting behavior that could indicate stress or passing over behavior in social scenarios. And we can expand the user study to include more users. And the benefit of our system for being real-time is it can enable just-in-time adaptive interventions. So future research could leverage our system to provide better smoke insulation strategies in real time. So thank you so much for listening to our Puffin project. This work wouldn't have been made possible without the support from my amazing collaborators and advisors, and I would be happy to chat more for collaboration and connect with you at the conference. Thank you.
Thank you. Thank you for the great work combining the software and the hardware. And our next presentation will be about the Parkinson's disease patient medication adherence monitoring. The presenter is Chongxin Zhong from North Carolina State University. And over to you, Chongxin.
Hello, everyone. I would like to present our work on adaptive multimodal fusion framework for smartphone-based medication adherence monitoring of Parkinson's disease. My name is Chongxin. I'm a PhD student at NC State University in computer science. And this is a collaborative work with Penn State University. Ensuring medication adherence is hard for Parkinson's disease patients. Study shows that 74.1% of PD patients reported lower adherence to the prescribed therapy. They have higher rates of yearly hospitalizations and total medical costs compared with other PD patients. Existing work to ensure medication adherence includes dosing devices, pill boxes, and easier dosing regimens. However, these methods still require patient self-management, making them error-prone. With the development of mobile technologies, monitoring medication adherence using a smartphone is feasible. One direction of existing smartphone-based systems for PD is to use a single sensing modality. They use different types of voice data or gait data. However, the data sets that using a single modality contain limited information. Sometimes it needs a personalized model for each patient, incurring more computational overhead. Works that use both gait and voice modalities rely on simple concatenation, which causes poor performance due to the low reliability of specific data modalities. The general idea of our work is to quantify the uncertainty of data from each modality of PD patients and combine them dynamically to create more comprehensive representations for better prediction accuracy. This is an overview of our work. First, we process the raw data with segmentation, window function, and Fourier transforms to transform raw data into spectrograms. And second, we quantify the uncertainty for each modality during the training of the unimodal classifiers and produce the dynamic fusion weights. Then we integrate the multimodal data dynamically and apply the gradient modulation for better results. Finally, we monitor the medication adherence of PD using the output multimodal classifier. For the uncertainty quantification, suppose we have n samples for gait and voice data, labels y, and the unimodal classifier for modality m that maps from samples to labels. We quantify the uncertainty using the energy score calculated based on the unimodal classifier's output. A larger energy score means the more uniform distribution, indicating the higher estimated uncertainty. We calculate the output using dynamic weights, which is calculated using the uncertainties of each modality, that is the energy score mentioned previously. The alpha and C are the hyperparameters that can be tuned for better results. The estimated uncertainty is regularized using the sample-wise loss to enhance its quality. It is regularized by learning the relationship between the average loss and the dynamic weight, ensuring that a higher average loss corresponds to a smaller dynamic weight. So the total loss is calculated as the loss after dynamic fusion plus the summation of each modality's loss before fusion and the regularized loss. Furthermore, we apply the gradient modulation based on the contribution of each modality after dynamic weighting. We have the discrepancy ratio between each modality contribution at teeth epoch. In our work, the gait and voice, the discrepancy ratio are the reciprocal of each other. It is calculated based on the contribution scores that use the softmax function. So finally, we calculate the gradient coefficient of each modality using the discrepancy ratio, ensuring that the modality contributes more to the output can be prioritized during the further training. After training, we can monitor the medication adherence. So the patients first need to input the scheduled medicine time in advance, and the system will collect patients' data passively 1 hour before and after the scheduled medicine time. It uploads data to cloud, processes and analyzes the data, and returns the result in a few minutes. Then it will send alert messages if medication adherence detected. We evaluate our system on a data set collected from 455 PD patients. We have about 150,000 gait samples and about 180,000 voice samples. The gait samples are segmented by gait cycles, and the voice samples are partitioned into 1-second chunks with patients saying vowels. The labels consist of before medicine and after medicine. So we pair the multimodal samples with the same label within the same day for the training. We have about 97,000 samples. Both the gait and voice samples are transformed into spectrograms. This figure shows the overall performance of our work. We can observe that the accuracy of the before medicine label is higher. This is because the efficacy of medicine may not be evident for some patients who have developed a drug resistance. These figures show the performance of our system in different demographic groups, such as gender, age, and years since initial hospital visit. The results shows that our work is independent from different biological factors and the progress of the disease. So this figure contains a comparison of the accuracy between different methods, including the methods that use single modality and the methods with a simple concatenation or only gradient modulation or dynamic weights. So the figure shows that our work outperforms other methods with the accuracy of 94.76%. Thank you so much.
Thank you, Chongxin. And our next presenter, Yida Zhang, will bring us work that estimate blood pressure from vibration signals using contrast learning. Over to you, Yida.
Yeah, thank you. Okay. Good afternoon, everyone. Thanks for being here. My name is Yida Zhang, a PhD student at the University of Georgia. And today, the paper I'm going to present is blood pressure estimation from vibration signal via cost-to-find contrast learning, feature selection, and synthesis. According to the data from the World Health Organization, cardiovascular disease claims more than 900,000 lives each year in the United States. And the blood pressure is the key health indicator for monitoring these conditions. As a result, accurate and continuous blood pressure estimation, especially during sleep, is crucial for the early detection and management of them. However, most existing methods either can't provide continuous measurements, or they will cause discomfort due to the body contact or raise concern about the privacy. So in recent years, more and more researchers have begun studying the relationship between the physiological vibration signals and the cardiac activities, including the blood pressure. And here are the two typical vibration signals, which are the BCG and SAG. And the contactless and passive nature of these signals allow for monitoring without discomfort or the concerns about the privacy. So it makes it a promising avenue for the real accurate and continuous blood pressure estimation. And currently, most approaches fall into two categories. The first involves manual feature engineering with digital signal processing, followed by the machine learning regression. But this requires expertise across different fields and extensive experiments. And the second one directly inputs the raw vibration signal into deep learning methods, but this often suffers from the poor generalization. Well, contrastful learning can potentially mitigate this, but most of them are designed for classification, overlooking the local feature for the regression. So to address this limitation and integrate the strengths of the DSP and the deep learning techniques, we propose a novel and effective framework to do the blood pressure estimation. And within the framework, we first designed the bed dot. It is a contactless and bed-based monitoring system that captures the vibration signal via geophone. And then the signal will go into two parallel branches, which are the feature selection and synthesis module, and the cost-to-fine contrast learning module. They will generate the synthesized features and the representations respectively, and finally we will fuse them to facilitate the blood pressure estimation. And I will introduce the three parts in detail. The first is the bed dots. It is a sensor we used to collect the vibration signal. And from the figure 8, we can find that it only consists of a Raspberry Pi, the ADC board, and the seismometer, which is a very simple structure with low cost. And when collecting data, the only thing we need to do is just attaching it to the frame of a bed. And the easy installation brings convenience to the user. And the contactless and passive nature ensures that it won't affect the user, especially where they are sleeping at night. And figure C shows how we monitoring and visualize the vibration signal. And for the feature selection and synthesis part, it has three components, which are the extractor, selector, and synthesis. And within our framework, the extractor is the TS field. It is the open source library for the automatic time series feature extraction. And to do the feature selection, we propose a novel selection layer. Unlike the traditional fully connected layer, the feature selection layer is one-to-one collected, which means that each neuron of it is only linked with one neuron of the input layer, and it is without bias. And to do the selection, we will apply the lasso regularization, also known as the L1 regularization on it. And because we know that the L1 regularization tends to set the parameter to be 0, so some certain weights in the selection layer will converge to 0 during the training. So it will exclude the unrelated feature from the further computation, and that's achieving the effects of the feature selection. And finally, we will use the multi-layer perceptrons to do the feature synthesis. And during the training, it will take the output of the select layer as the input and take the blood pressure value as the target label. And we will treat the second to last layer's output as the synthesized features. And to learn the robust representation with multi-scan information, we designed the cost-to-fine contrast learning module. It has two core ideas. The first is the hierarchical classification, and the second is the multi-layer contrast learning. And for a given batch of data, the first thing we need to do is use the encoder to transform the raw data into the representations. And then the hierarchical classification is employed to classify each representation into the corresponding intervals level by level in a binary manner. And here, the interval means the range of the blood pressure, and each interval will have two sum intervals at the next level, and the range of the sum interval is half of that of the apparent interval. And during the classification process, all the representations will go through one of the intervals of each level and finally reach the last level. And at the same time with the classification, we borrow the merits of contrastive learning to enhance the generalization ability of the representations and encourage them to capture the multi-scale information. And specifically, at each level, we will compute a contrastive learning loss by treating the representations in the same interval as positive pair, and that's in different intervals as negative pair. So the total loss for this module is the weighted sum of classification, regression, and contrastive learning loss. So to validate the effectiveness of our framework, we use three data sets, which are a public data set, a private data set, and a synthetic data set. And to simulate the distribution shift in the real world, we generate the synthetic data set, where the blood pressure range is different between the training set and test set. And the blood pressure value is a function of specific features in a heartbeat cycle. So through this table, we can find that the proposed framework achieves the lowest mean absolute error and standard deviation for both SBP and DBP on all three datasets. And the obvious improvement on the synthetic dataset indicates that it has the ability to learn the stable and generalized representations. And the ablation study demonstrates the effectiveness of both the two modules in our framework. And about the future work, we will conduct more experiments in diverse environments on various beds and with users in different status to validate and enhance the system's robustness. And we will also attempt to collect and integrate the tri-axis vibration signals for the blood pressure estimation. And thanks for your attention.
Thank you. Our next presenter, Aaron from Kansas State University, will talk about his work on the RAG pipeline for, is Aaron here? Okay, so Aaron will be talking about his work on RAG for dementia care practice education. Over to you, Aaron.
Oh, perfect. I don't think it will reach. Try this. Okay. Hello, everyone. My name is Aaron Cummings. I'm a PhD student at Kennesaw State University. And the work I'm going to be presenting today is a retrieval augmented generation pipeline for domain-specific applications. The case study was specifically in dementia care practices. Part of the motivation for this work is that of the people with, oops. Sorry, this screen is freaking out in front of me.
Of the people who have dementia or related ailments, 90% of them experience behavioral symptoms. Over 11 million caregivers provide dementia care, so like family members and professional caregivers. So this is a large group of people who need access to immediate information on interventions for behavioral symptoms that these people experience. So there's a distinct knowledge gap between caregivers and the publications that provide the interventions relevant to the behavioral symptoms that dementia patients experience. And these are also situations that are relatively high stakes where they need immediate solutions that are actionable. Patient is, and they also need a scalable solution in order to make the advancements in large language models and AI accessible to this domain and other domains more broadly. So some of the challenges that we see are a lack of domain-specific data when it comes to answering questions in domain-specific contexts. So there are existing data sets and models trained on general knowledge for question answering, and they tend to be less effective for domains where terminology is very specific, or some words might have different meanings than their more general usage. And there's also computational barriers. The adaptation of models requires a significant amount of computational resources, which is infeasible for a lot of people working on these projects. And a lot of the models will fail to prevent actionable responses that the caregivers can act on in a scenario where an intervention is needed. And without regular updates, the internal knowledge memorized by the weights of the models will become outdated relatively quickly. So our objective was to create a hybrid framework that utilized retrieval augmented generation and model fine-tuning to create a scalable and accurate domain-specific question answering system. So this system at the top level is the data preprocessing step, where we start with unstructured text, so a corpus of documents. In our situation, this was medical papers specific to behavioral interventions for dementia care. We process this data to create the retriever and the vector store that houses the data, as well as a collection of text chunks that are overlapping that feed into my next step here. In the middle is the question answer generation process. So in this step, we are taking the existing documents and using each of the individual chunks of body text to generate a question using a prompt to create the desired question format. So in this scenario, it would be scenario-based behavioral symptoms. So like someone is being agitated or someone is restless. And then we use that prompt to generate a question. And then based on survey feedback from professional caregivers, we're able to further refine that question by augmenting the prompt. And then likewise, we can generate an answer using the previous retriever and vector store to get an answer that's based in multiple sources. And then likewise with survey-based data, we can improve that prompt based on their feedback. And then using that corpus of question and answer pairs, we can then train our model to better facilitate the question answer paradigm rather than other tasks. sorry. So the output of the entire framework would be both a data set of question-answer pairs that are specific to the domain, as well as a model that's been tuned on those questions and answers. So for data preparation, we use a tool called Gorbid. This tool allows us to parse out any extra formatting in publications. So we just want to use the body text. This will save computational power and storage. And then it's chunked into overlapping segments so that it makes sure that all of the potential ideas and concepts presented in the work are captured, and no idea is segmented across multiple chunks. And then for fine-tuning, our focus was on parameter-efficient fine-tuning for accessibility to the model and the framework. So by using PEFT adapters, parameter-efficient fine-tuning adapters, and quantization, we can freeze the model and reduce the precision of the parameters to allow it to be more computationally effective or efficient when training on our question-answer paired data set. So this allows relatively small models to be accessible for niche domains where they need high performance on very specific tasks, but lack the computing power to host their own models. So, and then finally, the retrieval augmentation is pretty much the workflow that most people are familiar with. Documents are embedded in a vector store and then retrieved based on dense similarity. And what this allows for is a reduction in hallucination and an increase in relevance in the generations that the model responds with. So the results of our experiment found that basically with fine-tuning and retrieval augmented generation combined, we saw the best contextual relevance to responses that were vetted by caregiving professionals. But we were also able to see that there's a direct trade-off between retrieval augmented generation and fine-tuning, that they each have their own nuanced effects on how the model responds, be it precision versus the ability to recall information. And then we also saw that the combination of the two in the framework provided a more concise output more frequently. So shorter responses with more contextually relevant actions that the caregivers can give. So just in closing here, the framework provides an increase in contextual relevance in the responses and a higher semantic coherence, as well as reduced hallucinations. And yeah, happy to answer any questions.
Thank you. Our last presentation is given by Pegah from Kansas State University. She's going to talk about a multimodal large language model for NEOA progression estimation. Let's give our warm welcome to Pegah.
Thank you. Is it touch screen? Oh, thank you. Okay, hello everyone. Good afternoon and thanks for joining me today. I'm Pegah Ahadian, PhD candidate in computer science at Kent State University and Cleveland Clinic Biomedical Engineering Department. Today I'm going to talk about our recent work, OA agent, multimodal LLM agent for predicting knee osteoarthritis progression. This work is a collaborative effort between Kent State, Cleveland Clinic, and Brookhaven National Lab. Let me start by why this research matters. So
Knee osteoarthritis affects over 300 million people worldwide and stand as a leading cause of disability. The significant challenge, oh, sorry. Yes. So the significant challenge that we face in osteoarthritis is that the prediction of progression is challenging. While we can diagnose the osteoarthritis, its prediction is very challenging, and it makes a clinician to make timely intervention that could prevent severe disability. So our focus has been on developing explainable multimodal AI system, especially for progression prediction. We have created OA Agent, an AI system that combines clinical data and medical imaging in this paper only X-ray, no MRI or CT scan, and large language model with the core of reasoning, Llama 3.2, and to enhance both prediction accuracy and clinical decision making. Our main components in this work, first we created pipeline that integrate both clinical variable and medical imaging. Second, we developed two AI models. And then the last component is an interactive LLM agent that explains model prediction in clinically meaningful terms. This research has two impacts. We are enhancing outcome for patients with osteoarthritis, and we are helping early intervention for cause of progressive condition. So why is OA agent important, especially in today's healthcare landscape? Osteoarthritis progression prediction is complex and requires several capabilities. First, we need to integrate a heterogeneous data, we need to understand the temporal disease progression, especially when we talk about joint space width. We need time series of like different visit of joint space with size over time. And also transparent and interpretable decision support for clinician and their decision making is very effective. For clinical relevance perspective, early prediction of osteoarthritis progression is a game changer because it enables a timely intervention that can significantly reduce the risk of severe disability. And as OA is a leading cause of pain and mobility issue, the social impact of better prediction is very important. Our innovation in this work has two key areas. First, we combine clinical variable and imaging for more comprehensive prediction. Second, our LLM enhance explanation, which make prediction transparent and understandable for healthcare professionals, which bring the gap between AI capability and clinical practice. So developing this system wasn't without challenges. Here is some of those challenges that we face. First of all, there is a lack of unified AI tool for multimodal data in healthcare domain, and most existing approaches focus on either imaging or just clinical data. Second, we face limited availability of high quality label data. Medical data set, very often they are incomplete, inconsistent, or lack the temporal follow-up which is necessary for progression prediction. There's a significant challenge deployment and EHR data integration because most of AI models these days, they trained on static data, not dynamic, messy EHR data. So, and multimodal data fusion is complex and sometimes, most of the time, is insufficient. And then AI expert reasoning, they can just identify the pattern, but can't explain their decision in clinically meaningful way. And finally, the challenge of explainability in AI models. Healthcare provider, they need to understand not just what the model predict, but why it makes those predictions. So the system workflow and how does OA agent work? First of all, we have two primary streams. First is our clinical data. Our input features include joint space width at baseline, 12, 24, and 36 months, Kellgren-Lawrence grade, which is a severity grade, BMI, and age. Our target variable is a group type, which is classifying patient as either a progressor or non-progressor condition. We have processing, like including missing data imputation, normalization, and class balancing to ensure that we have a robust model performance. Second is about the X-ray images data. We work with 512 by 512 RGB images that are labeled as progressor and non-progressor. And we have done pre-processing, including resizing, normalizing pixel values, and converting to tensor to be ready for a neural network. And two models that we use for this work is neural network for clinical variable. It's a multi-layer perception with dropout layer to prevent overfitting. And it takes clinical feature as input, and the output is a likelihood between 0 to 1 for osteoarthritis progression. Our X-ray model employ a convolutional neural network that processes image through convolutional layer to extract joint abnormality and a spatial pattern. The output, again, is a likelihood of progression based on learned visual feature and correlation with the disease. It's mostly a correlation between joint space and its changes. And the last component, which is the most important one, is a LLM agent, the core of interactive reasoning. Our LLM agent operate using iterative thought action observation cycle. We initiate the environment very similar to reinforcement learning, but instead of action and reward, we are using these thought action and observation cycle. And this cycle can actually improve the diagnosis quality because it doesn't just run one time, but also it can trigger and rerun several times to get to the point of like the best performance. The agent retrieve relevant patient data from both clinical and imaging, and then process them and call the models for prediction. And finally, it refined the reasoning through multiple iteration, building a comprehensive and understanding the patient condition. The output is a explainable output, like as an example here, that the model can say based on this JSW and over 24 months and KL grade, for example, 2 or 3, combined with like imaging feature showing cartilage loss, then the have a likelihood of progression. And here is a diagram of OA agent, which I already explained. I think I don't have time to explain it again. And for the result, the performance performance and validation of our system, we used, here we presented just a UC of 82, and the confusion matrix for our X-ray model show the balanced performance in both classes, and more importantly, the LLM show the effective reasoning step, validate across multiple test scenarios, and the whole system show the transparent decision-making process that a clinician can follow and understand, that you can see in this part, which is a process of asking questions based on some clinical variable, and the model start processing those a number and make it like vectorize it, and then train the model, and then query to the database and retrieve the X-ray related to that patient, and then evaluate if based on the X-ray and based on those clinical variable, the case is close to progressor or non-progressor. And the benefit of OA agent is that first, we significantly enhance explainability for sure. And second, we improve physician or user interaction, which user can query how the AI arrived at the decision, and creating a collaborative diagnostic environment rather than a black box prediction system. Third, our data analysis approach utilizes both imaging and clinical, this increases the diagnostic accuracy. And fourth, our system offers a scalability, which it's applicable for other chronic disease. And as an achievement and conclusion, we integrated two different data types. We used chain of thought reasoning with case-based explanation and show the interpretability in this work, build an interactive reasoning agent, and this work in this framework is adaptable for other chronic diseases, as I mentioned before, and adaptable to new data and features. As a future work, we plan, and it's actually ongoing, to employ X-ray, MRI, and biomarkers, and integrating real-time data input from EHR also, and enhancing LLM reasoning for more detailed clinical explanation. Thank you.
Thank you.